Hello everyone, this is Lecture 6 of ComSci 123, Maps and Dictionaries. In today's video, we will talk about the map ADT, the dictionary ADT, and how to implement them using arrays and linked lists. Previously, we mentioned that there are two types of ADTs, that would be the linear ADT and non-linear ADTs. And so far, we have seen linear ADTs in our course. So for linear ADTs, they have to follow these four properties. First, there should be a unique first element. Second, should be a unique last element. Next, each element should have a unique predecessor except the first item. And each element needs to have a unique successor as well except the last item. Okay, so all linear ADTs have to follow these four properties. So for the linear ADTs that we have seen so far, we have discussed 6 ADTs so far. So first, we have the stack, which follows the last in, first out method. So the last item that you push in would be the first item that you would pop out. Okay, so you have three main methods for stack. You have the push, pop, and top. And then next, you have the queue, which follows the first in, first out method. So the first item that you in queue, which is in this case A, would also be the first item that you would push out or dequeue. Okay, so you in queue at the back and then you dequeue at the front. So you have the in queue, dequeue, and then the front method to check what item is at the front, right? So that's the queue. And then you also have the double-ended queue or the deck. And this time, instead of only in queuing at the back and dequeuing at the front, you can insert and remove both at the front part and the back part. So you can do insert first, remove first, insert last, and remove last. Okay, so that's the double-ended queue. And then you also have the vector ADT, which uses the concept of rank. And then if you remember, rank just means that how many items are in front of you. So for item C here, which is rank 2, it means that there are 2 items in front of it, and that would be A and B. Okay, so you can insert at rank, replace at rank, remove at rank, and get the item at a certain rank. Okay, so you access the items based on their rank. And then you also have the list ADT, which has the concept of knowing the item before you or after you. So for example, A is before B and B is after A. Okay, so it doesn't know the rank, it doesn't know where it is in the whole list, but all it knows is that I have an item before me, I have an item after me. Okay, so you have a lot of methods here, like is this position the first, is it the last, what is the first position, what is the last position, what is the position before me, after me. You can insert first, insert last, insert before a position, insert after a position, and then you can do remove, replace item, and swap items. So these are all the methods for the list ADT. Okay, and then finally, we also had the sequence ADT, which was just a combination of the vector and the list. Okay, so you can do things based on their rank or based on their position, so before or after. And then you also had 2 additional bridge methods, at rank and rank off, so that you can switch between from rank to position or from position to rank. Okay, so those were the 6 linear ADTs that we have discussed so far in ComSci 123. Now, if one of those 4 conditions earlier that we mentioned are not true, then the ADT is non-linear. So if there is no unique first element, if there is no unique last element, no unique predecessor or unique successor for each item, then it could be non-linear ADT. Okay, so if even just one condition is not met, then it's already a non-linear ADT. So we have examples of non-linear ADTs here. So you have the hash table, you have the tree, you have here a map, you have here a priority queue. Okay, so for example, here in the tree, this is non-linear because, for example, A has two successors, which is B and C, which are its children, right? So it doesn't have a unique successor, so it's already non-linear. And then for the map, for example, there is no concept of order here. We don't know if John was the first item added here, or it could be the last item, or it could be added in the middle. So there is no concept of order here, so there is no first, last, successor, predecessor. Okay, and then for the priority queue, for example, let's say that priority 2 Bea was the first in line, but Jake, which has priority 1, maybe he's a senior citizen, could be taken out of the priority queue before Bea. Okay, so even if Bea came first, Jake could be taken out first because he has a higher priority. Okay, so we'll learn more about this as we go on with the course, but for now, just know that if one of the 4 conditions is not met, then the ADT is non-linear. So this is the list of all the non-linear ADTs that we will learn in ComSci 123. So in today's video, we'll focus on maps and dictionaries, and then in the next videos, we will learn about hash tables, trees, binary search trees, priority queues, and heaps. Okay? So let's start with our 7th ADT now, which are the maps. Now, we're not talking about this type of map here, or this map, okay? The maps that we're talking about is the map ADT, which is a searchable collection of key value entries. So you have a pair, a key value pair, and we call this collectively as an entry. And we can search entries, we can insert entries, and we can delete existing entries. So you have the 3 basic operations: search, insert, and delete. Now, the keys are what you need, what you use to look up the entries. Okay, so if you want to look for a certain entry, you use the key, and the keys are usually strings or numbers that is associated with a value, so that it's easier to look up. Now, the value could be any type of object that you want to save. Okay, but the key characteristic for the map ADT is that multiple entries with the same key are not allowed. Okay, so this means that there should only be a one-to-one mapping. Okay, so one key can only be mapped to one value. Okay, so this means that the keys should be unique. Okay, the values, however, need not be unique. So multiple keys could map to the same value. Okay, so what do we mean by this? So here's an example of a key value pairing wherein the keys are unique but the values may not be. So for example, our keys here are the countries. Okay, so you have Turkey, Spain, Greece, China, the US, and India, and the values are the currency that they use. So for Turkey, it's mapped to lira. For Spain and Greece, they're both mapped to euro. For China, it's yuan. For the US, it's dollar. For India, it's rupee. Right? So you have a key which maps to a value, which is the currency, and you'll notice Spain and Greece are both mapped to euro. Okay, so the values are not unique, but the keys are unique, because in this case the keys are the countries. Okay, so yeah, here's another example. You have the name and the score map. So let's say you have a quiz or a test, and then the name of the students would be your keys, and then the values would be the score, right? So you will see this notation in this video a lot. So you have, for your entries, it's made up of 2 things, right? You have the key and the value. Okay, so this whole thing here is one entry. Okay, so this one is one entry, John 15, this one is another entry, Jane 20, Luke 12, and so on. So each one here is one entry, wherein the names are the keys and the scores are the values. Okay, so yep. So those are examples of maps with their keys and values. Now, where can we apply maps? So for applications wherein you need unique keys, so maps would be applicable. So for example, student number and then exam score. So in the previous example, name might not be a really good key because there could be students having the same name. Okay, so there would be collisions or conflicts, right? So it's much better to use a key that would be unique to each entity. So in this case, that would be your student number, because the student number is unique to each student, right? So student number to exam score is one example. And then you can also have employee number to employee name, right? Wherein the employee number is the unique key, and then map to the name of the employee. And then you also have plate number, vehicle owner, right? So plate numbers are unique in a certain country, and then it could be mapped to a vehicle owner who is the registered owner of the vehicle, right? And then in sports, in a basketball team or in a football team, volleyball team, jersey numbers are unique also. So the jersey number is the key, and then the value would be the player name. So who owns that jersey number? And it's also not limited to just numbers. As I mentioned, it could be a number or a string. So if you're maybe counting word frequency, so the word would be the key, and then the frequency or the count of a certain word in, let's say, a paragraph or a certain text would be the value. Okay, so that is another example of a map application. Okay, so that's the applications for maps. Now let's move on to the interface of the map ADT, or the set of methods that this ADT should be able to handle. Okay, so this is the full set of methods for the map ADT. So you have the size, is empty, get, put, remove, and then 3 iterators, keys, values, and entries. And then we'll go through each one to discuss them in detail. Okay, starting with, of course, the size and is empty, which is pretty self-explanatory for by now. So size returns the number of entries in the map, so how many entries are there. So it will return an integer or a number. And then is empty will return true or false depending on whether there are entries in the map or not. Okay, is it empty or not? So yeah, that's pretty straightforward. Next is get. Okay, get k, and k here is a key. Okay, so if the map has entry with key k, then you return the associated value. So you're given a key, and if it exists in the map, then you should return whatever value it is mapped into. Okay, however, if the key k does not exist, you return null, because, well, the key does not exist. Okay, so that's why you return an object here. So it's either the associated value or null. Okay, so that is basically the search method, get. Next is the method put. So put kv, where k here is the key and v is the value. So first you create the entry with key k and value v, and then you insert that entry into the map. Okay, however, since we need to ensure that the keys are unique, we have to check if the key k exists already. So if the map already has an entry with key k, then you need to return the old value associated with k and overwrite that value. Okay, so we need to overwrite the old value with this new value here and return the old value. Does that make sense? However, if it doesn't exist, so it's a new entry, then we don't return anything. So it return null. Okay, since there is no old value to return. Okay, so that is the insert method put. Okay, and next we have the deletion method, which is remove. So remove k, so it also passes in the key k, and if the map has entry with key k, remove it from the map and return the associated value. So whatever value key k was mapped earlier, we need to return it also, since we have the object return here. Otherwise, if the key does not exist, then we will not return anything, and we won't remove anything either. Okay, so we only remove if the key k exists. Okay, does that make sense? Yeah. And then finally, we also have the 3 iterators. But what are iterators? Iterators are basically functions that are used for traversing or iterating over a collection of items. So you go through a collection of items one by one. Okay, so you iterate through them. So the 3 iterators are keys, which you use to iterate over the map's keys, values for the values, and entries for the entries. Okay, so we'll see this in an example later. But basically, you go through either the keys, the map's keys, values, or entries, depending on which function you called. Okay, so those are the methods for the map ADT. So let's go through an example. So we have a map here with 4 entries. So the entries are A10, B2, C3, D7. Okay, so this column here is the keys, and this column here are the values. Okay, so let's go through all of these methods here and try to see what happens if we call them. So for the size, since there are 4 entries, size will return 4, right? Now if you get B, so the key that you want to get is B, so look for B here, and we found it here. So we'll return the associated value, which is 2. Okay, so B is mapped to 2, so we'll return 2 here. Now if we get X does not exist in the map currently, so we will return null because there is no key X, right? Now if we want to insert, we will use the put method. So put E14. Now let's check first, does E already exist as a key? Well, it's not, so we can safely add it here as a new entry. So we can add E14, right? And what will we return? Well, we'll return nothing, also null, because it did not overwrite anything. Now for our next one, put A11. Well, A already exists, right? So it's here as the first entry. So what we'll do is we will overwrite this. So we'll write 11 here and return the old value, which was 10. Okay, so if the key already exists, we will overwrite it with the new value and return the old value. Okay, next, remove C. So if we remove C, we'll look for C, and we found it here. So we'll remove this entry here, so that should be erased out of the map now, and return its old value, which was 3, right? Now if you remove X, there is no X, so nothing should happen, so we'll return null, and we didn't remove anything. Now for the keys, this would be the iterator for the keys, so they should return the keys, which are A, B, D, and E. Now notice C is not included anymore since we have removed it previously, right? Now for the values, we'll do the same thing. We'll iterate through the values, so that would be 11, 2, 7, and 14. So those are the current values existing in our map. And then finally for entries, that would be the 4 entries, so that would be A11, B2, D7, and E14. Okay, so those are the 4 entries that are left in the map. Okay, so that's it for the example of map. So it's pretty straightforward, right? If you get, you just look for it. If it exists, return the associated value. If it does not exist, then you return null. For put, check first if it exists already, because if it does, then you overwrite the existing value and return that old value. If not, then you just safely add it as a new entry. Then for remove, of course, you can only remove if the key exists, and then if it does, return the old value. If it does not, then you don't have to remove anything. Okay, so that is the map. Okay, so let's clear everything first. So that is map. Next, let us go to the next ADT. So this is already our 8th ADT, which is the dictionary. So it's not exactly this type of dictionary, but it's somehow related, okay, as we'll see in a while. So the dictionary ADT is also a searchable collection of key value entries, just like our map, right? So it also holds key value entries. You can also search, insert, and delete entries, just like the map as well. But the main difference with the map is that entries with the same key are now allowed. So remember, in the map, the keys have to be unique, right? So if the key already exists, you have to overwrite it. However, in the dictionary, you're allowed to have entries with the same key. Okay? So, yeah, that's the main difference. So it's similar to a real-world dictionary, wherein one word could have multiple definitions, right? So one word could have the verb definition or the adjective definition. So that's dictionaries. Now, in Python, there is actually a dictionary data type, right? So I'm sure you have encountered this before in ComSci 11. So for example, A is mapped to 5, B is mapped to 6. However, it turns out that this is actually not a dictionary technically. It's actually a map, because the keys are unique in this data structure. So for example, if you add A6 here or A4, it will not add a new entry. It will actually overwrite the existing entry for A, which is A5. So if you set this to A4, then this will become A4 and not add a new entry. So this is actually a map and not a dictionary technically. They just call it a dictionary, but it's technically a map. Okay? So don't be confused by that. So what are some applications for the dictionary? So of course, you have the word and then the multiple possible definitions, and then you have the name and contact number. So for example, on your phone, you could have John, who's from work, have this number, like say 0977 ... whatever. And then you can also have John, who is a friend from high school, have this number 0921 ... So you have two Johns with multiple contact numbers. So a way for you to disambiguate this might be like John from work and then John from high school, right? So you usually do this just so you don't confuse the two with each other. However, even if that's the case, sometimes there could also be like, si Jane has a globe number, so 0977 ... and can also have a smart number 0921 ... So for one person, you have two numbers assigned to them. So this is a dictionary because you have one key. So this is also Jane, right? So you have two entries, so Jane with the globe number and Jane with the smart number, and they have the same key, right? So that is a dictionary application. Okay. Next, username and donation amount. So for example, in streaming platforms like Facebook or Twitch, you have usernames and then how much they donated, because users can donate multiple times, right? So we'll see that in our example later, but this is also another application of dictionary. So basically, when you have a problem where you don't need unique keys, then you can use dictionaries for that. Okay? So let's now look at the interface for the dictionary ADT. So what are the methods that the dictionary ADT supports? So you have the following: size is empty, insert, remove, find all, and entries. So as usual, we'll go through each one to discuss it in more detail. So of course, we start off with the basic ones, which is the size, which tells you the number of entries in the dictionary, and is empty, which returns true if there are no entries in the dictionary. So this should be pretty self-explanatory by now. But the important ones are the following. So first, you have insert. Okay, so when you want to add a new entry, So you pass in two things, insert k, v. So you create an entry with the key k and the value v, and you insert the entry to the dictionary and return it. Okay, so you return the entry that you just added. Okay, so take note that we're not checking if the key already exists, because this is not a map. Okay, so even if the key already exists, it's fine, just add it as a new entry to the dictionary. Okay, so it's pretty forgiving. Next, you have remove method, but take note that this one takes in an entry this time, so entry e, not a key. Okay, so you remove the entry e from the dictionary. So compare that with the maps remove method, wherein you need to pass in a key. Okay, but this time you need to pass in an entry e and not a key k, because there could be multiple entries with that key, right? So if you don't specify exactly which entry, then it might be confusing. Okay, so I'll show you later in an example. And you actually don't return anything. Okay, so that's why the return type here is void. And the next, you have the search method, which is called find. So find k, so you pass in a key. So if the dictionary has entry with the key k, then you return that entry. Okay, otherwise you don't return anything because the key does not exist. However, it's a little trickier in the dictionary because there could be multiple entries with this key k that you passed in. Okay, so if there are multiple entries with key k, then you return one entry only. Okay, so which entry, that would be dependent on how you implemented it. So it's not necessarily the first entry that you added, it could be the last entry that you added. So it's not guaranteed. So it's dependent on how you implemented it. As long as that entry has this key k, then it could be returned. Okay, so yeah, we don't know which entry exactly will be returned, but as long as it has this key, then it should be fine. Okay, so that would be find k. Okay, next we have two iterator methods, find all and entries. So find all will take in a key k, and it will iterate through all entries that have this key. So if there are multiple entries with the key k, then it will go over each one, through iteration. And then finally, for the entries method, it's an iterator for all dictionary entries regardless of the key. So it will just go through all entries. Okay, so that would be the set of dictionary methods. So let's take a look at an example of a dictionary, and this is the example that I mentioned earlier, with the usernames and the donation amounts. Okay, so for example, user A here donated 50, user C donated 100, user B donated 25, and so on. Okay, so these are the keys and these are the values. Okay, so you'll notice that some users have donated multiple times, like user A who donated 50, and then here another 50, and then user B donated 25 and then 50. So you can do that since this is a dictionary. So let's try to go through each one of these methods here and try to figure out what will happen if we run them. So for size, since we have 6 entries in the dictionary, this will return, well, 6, right? And then next, insert user C50. So this will just create a new entry, which is user C50, and then add it as a new entry here. So that would be user C with 50 as the donation amount. Okay, so it will also return the newly added entry that we just created here. Okay, now next we have remove user C 100, and notice that we passed in a whole entry and not just the user C key. right? So that would be this entry here, user C100. So we'll actually remove this. Okay, so I'll cross this out to signify that it's not part of the dictionary anymore. And why do we need to pass the whole entry? Okay, and not just the key. So remember in map, you were just passing in the key, like remove user C, right? So you can do this in the map because you are assured that this key was unique. So if it did exist in the map, you just need to remove that one entry that has this key. However, in the dictionary, you are not assured of that uniqueness, right? So for example, here, user C has actually two entries. So this one, 100, and then this one, 50. So if you just passed in user C, remove user C, we're actually not sure whether you mean to delete this 100 entry or this 50 entry, right? So to avoid confusion, just pass in the whole entry that you need to remove, okay? So that's why we passed in user C100 here and not just the key, okay? So yeah, so after removing this, let's go through find. So find user A. So there are actually two user A entries that can be found here in the dictionary. That would be here, user A50, and then another user A50. Okay, so depending on the implementation, we don't know if it's the first one or the second one that will be returned, but since they are both user A50s anyway, so we are sure that this will return a user A50 entry. Okay, now for find user D, since there's only one user D entry here, so we are sure that it will return user D30, right? So user D30. Now for user X, there is no user X entry here, so this will return null. Okay, and again, if we run find user A the second time, well, it could maybe return the first one again, or maybe this time the second one, but either way, this will return user A50 still. Okay, now if you were to find all user B entries, there are actually two here, right? So where are the two user B entries? You can find them here. So user B25 and user B50. So if you're to find all user B, so this would be an iterator, so it will return user B25 and user B50. Okay, and then finally for entries, this will just return all of the entries, right? So we'll go through each one. So you have the user A50, user B25, user B50, and then user A50, and then user D30, and finally user C50. So there are still 6 entries because we did insert one, but we also removed one, right? So yeah, those are all the entries that could be returned if you call the entries iterator. Okay, so that's an example of the dictionary at work. Okay, so let's clear everything here. Okay, so that is the dictionary. So to compare the maps and dictionaries with their similarities and their differences, so both of them use entries, right? So key value pairs. So the keys are what you need to use to look for the entry itself. So keys are used for lookup, and then the value is the actual value that you want to store, right? So both of them use entries, but the difference is that maps need to have unique keys, whereas dictionaries can allow the same keys. And then for their methods, they both have size and is empty. And then for map, the insert method is put key value, And then for dictionary, it's called insert key value. The difference here is that for put, you need to make sure that key does not exist, right? Already. Because if it does, then you need to overwrite it instead of adding a new entry. Okay? For insert, it doesn't really check that because you can just allow the same keys, right? And then for remove, which is the delete method, so they're both called remove in both map and dictionary, but the difference is in remove for map, you pass in a key. In dictionary, you pass in an entry. Okay? Because there could be multiple entries with the same key, so just to avoid confusion, just pass in the entry that you want to remove. Okay? Now for get, for the search method, you have get for map and then find for key, find for dictionary. Okay? The difference here, of course, is that for find key in dictionary, you're not assured of which entry will be returned because there could be multiple entries having the same key. But for get in map, of course, you're assured of which entry will be returned because either the key is there or not, right? And then for maps, you have the three iterators, keys, values, entries. But for dictionaries, you only have the find all for key and then the entries. Okay, so that is the idea behind the map ADT and the dictionary ADT. So that will be the first part of this lecture, and of course the second part is coming, which should be the implementation part. Okay, so now we are ready to implement the map ADT and the dictionary ADT using arrays and linked lists. Specifically, we will be using doubly linked list in this implementations since it would be more convenient. Okay, so make sure first that you understand the ADTs, the theory behind it before proceeding with the implementation part of the lecture. Okay, so first let's take a look at the DLLMap implementation, wherein you try to implement a map using an unsorted DLL or a doubly linked list. Okay, so you just store the map entries to the DLL in an arbitrary order, so maybe in the order that they are added, so you don't sort them. Okay, so this is an example of the DLLMap. So let me discuss first the notations. So the DLL nodes would look like this, right? So you remember the DLL nodes from your doubly linked lists. So it has three things, right? So a link to the previous node, a link to the next node, and the item itself that it is holding. Okay, so you have the get preview, set previews, get next, get item, set item. So you remember those from our previous lecture on the doubly linked list, right? So the DLL node will look like this. So those are the yellow ones here. And then the entry would look like this. So you have the key value separated by the colon and then enclosed by the angle brackets here. Okay, so this would be how the entries would look like. Okay, so key value here. So those are the blue ones here. And for our map example, we only have 3 entries, so this is just a small example. So you have B2, A10, and C3. So for the DLL map, you have the DLL here with the head guard and the tail guard. So you remember the sentinels that guard the end and the front and the back of the DLL. So you have 3 entries, so you also have 3 DLL nodes here. And each DLL node will hold 1 entry. So for the first node, that would be B2. For the second node, that would be A10. For the third node, that would be C3. Okay, so this is an example of the DLLMap implementation. Now, what would happen if we ran this 6 methods here in total? So let's see. What would happen if we tried to get B? Okay, so this is a search method, get B. So we'll start at the head guard right here, and to look for B, then we'll have to traverse, right? So you'll go to the next. Well, is this B? Well, fortunately for us, it is already the entry with key B. So we'll return this value here, which is 2. So we found it right away. Okay, So next, how about if we searched for X? Okay, so this one had 2, right? If we search for X, so same as usual, we start at the head guard, go to the next. Is this X? No. Is this X? No. Go to the next one. Is this X? No. Until we reach the tail guard, and at that point, since we've reached the tail guard, then we are sure that key X does not exist, so we'll return null for this one actually. Okay, so yeah, so that is the get method. Now how about for put? For put, let's say we put D7. First we need to make sure that the key D does not exist, right? So we have to search first for the key D, right? So start at the head guard, go to the next. Is this D? No. Is this D? No. Is this D? No. And then we'll reach the tail guard. So we are sure that D does not exist. So what will we do in this case? In this case, it is safe to add the D7 entry as a new entry in the map, right? So we will add a new entry. So we'll create a new node here, a new DLL node at the end. Okay, and then we'll add the entry D7 inside. So this is D7, and then we will add it to the map. So how will we add that? So we will link C3 here and link D7 here, then link D7 to the tail guard and the tail guard to the new node, and then this 2 would be erased already. So these 2 links won't exist anymore. Okay, so yeah, so that is how we add the new entry D7 to the map. Okay, so you add a new DLL node and then add it maybe to the back, or you can also add it at the front if you want to, since it's unsorted, but in this case I just added it to the back. Okay, now how about if we try to add or put A11? So again, we need to make sure that A does not exist already. So we start at the head guard. Let's check. Is this A? No. So let's go to the next. Is this A? Well, it is actually A. So we won't add a new entry. We will just overwrite this existing one. So instead of 10, we'll return. We will change this to 11 and return the existing value, which was supposed to be 10, right? So it will return 10. Okay, so A11. Okay, now how about for remove? What if we remove A? So in order for us to remove a key, of course we have to look for it first, right? So we'll do the same thing. So we start here. Is this A? No. Is this A? Well, yes, it is. So what we will do is, since we've found that the node to delete, okay, so we'll have to delete this one, the whole thing. And now, since we delete this node, we have to reconnect some of the nodes that will not be connected anymore. So actually, this one, this link here, will go to C3's node, and this link here will instead go to B2's node. Okay, and then this 2 links here won't exist anymore. Okay, so that is essentially how you delete the A node. Okay, by relinking B2 and C3. Now how about if you remove X? Well, X is not existent, so if we start from here, is this X? From head guard, you go to the next. Is this X? No. Is this X? C3? No. And then you go to D7, still not. And then you go to the tail guard, still not X. So there's actually nothing to remove. So yeah. So that is how you do things in the DLLMap. So you should be quite familiar with it already by now, since you've experienced some implementations using DLL, right? So yeah, that's DLLMap. Let's try to clear everything first. Now, how about the performance of the DLLMap? So for the running time, all three methods, get, put, and remove, will actually take O of n in the worst case. And why is that? It's because all three methods will involve traversing the DLL to look for the entry with the given key. So for example, for get, at the worst case, it could be at the end of the DLL, or it could not exist at all. So you would need to traverse through the whole DLL to make sure that you did not miss out on the given key, right? So for search or get, you will have to traverse through the DLL to look for it. For put, you also need to search first if that key already exists, right? So it might also take going through or traversing through the whole DLL to make sure that, hey, this key does not exist. And once you reach the tail guard, then that is the time that it's safe to add this new entry, because if you already found it previously, then you would have overwritten that node already, right? And then for remove, the same thing. Before you can remove it, you need to look for it. So it also needs to traverse through the DLL to look for the entry. So all three methods will take O of n, since you need to linearly go through each node one by one. Okay? For the memory, it's also O of n, because of course you have n nodes, one DLL node for each entry of the map, right? So it's also O of n, which is linear time. Linear memory. So you can tell that it's only effective for small maps, because if the map already has, let's say, 1,000 or 1,000,000 entries, then it would also take, let's say, 1,000,000 time steps at the worst case for get, put, and remove, right? So your running time and your memory scales with your with the size of the map entry. Okay, so it's only effective for small maps. Now, how about if instead of an array of DLL, we used an array instead? So what if we used an unsorted array? Will that kind of improve the performance? Okay, so it has the same, we have the same map here, B2, A10, and C3, and instead of DLL, we just use a simple array. Okay, so what would happen? Well, actually the same problems exist if we use an unsorted array, because if we get B, for example, what would need to happen? So we'll start at index 0, right? And well, fortunately we had B here already, so this will return 2, right? But what if we get X, which does not exist? Okay, so we'll start at index 0. Is this X? No. Is this X? No. Is this X? No. And until we reach the end. So we return null, right? But we have also traversed through the whole array, right? And then if we put D7, the same thing. We need to make sure first that this D does not exist already. So is this D? No. Is this D? No. Is this D? No. So now it's safe to add D7 here, right? And then for put A11, we need to make sure. So B is not A. A is here, so we'll actually overwrite this with 11. So we changed the underlying data structure from a DLL to array, but the same problems exist. We still need to traverse either the DLL or the array to make sure that the key does not exist. And then additionally, here's one more problem, or not really a problem, but another thing that you need to do if you are using an array. For example, if you remove B, okay, so we'll start here at 0. Well, now you can remove B, right? But then B would become empty here. Okay, so if B becomes if index 0 becomes empty, we need to actually move things forward, right? So that there won't be any holes in our array. Okay, so you additionally have to shift items forward so that you don't have a hole. So that's additional time steps. So all of this methods here, get, put, and remove, still run in O of n running time. Okay, because of the traversing. So from here to here to here to here, to make sure that either the key exists or the key is not already pre-existing, so that we have to overwrite it or we have to create a new entry. And then for remove, we have to search for it, and additionally we have to move entries forward if there are holes that we need to fill in, right? So even if we switched out the DLL for the array, it's still the same running time. It's still O of n. So yeah, it does not really improve. It even worsens because of the shifting of items on remove. Okay, so that's it for implementations of maps for now. Let's try to move on to the dictionary. Okay, so for dictionary, let's try it with an unsorted DLL. So DLLDictionary is implementing the dictionary using an unsorted DLL. So an example of this would be like a log file of the username donations that we used in the dictionary example earlier, right? So we have here that example. So we have the dictionary of size 6. So user A donated 50, C 100, and so on. Okay. So similarly, we would use the DLL, right? So you still have the head guard and the tail guard, the sentinels here, the DLL nodes, and each DLL node has an item which is the entry. So you have the A50, C100, B25, B50, and so on. Okay, so this is the DLL dictionary. Okay, so let's see what will happen for each of these methods listed here. For insert C50, well, for dictionary, we don't need to make sure that keys are unique, right? So if you want to insert an entry, you just need to add it at the end, right? So I have C50 here, and to add that to our DLL dictionary, we'll just need to create a new DLL node, which looks like this, and then we add the entry C50, right? So that would be C50, and then we have to add it to the actual DLL, right? Because this is just an independent DLL node, we have to actually link it. So here, the D30, instead of pointing to the tail guard, we'll have to link to this, and C50 will have to link to D30. And then the tail guard, instead of linking to this one, so we'll just remove this one, and then for the tail guard, it will have to link to here, and C50 will have to link to the tail guard. Okay, and this way, C50, the node for C50 is already part of the DLL dictionary, since after D30 you go to C50, and then after C50 you go to the tail guard, right? So it's now linked to the actual DLL dictionary. Okay, now how about if we remove C100? So for C100, to remove this, we have to start from the head guard, right? So from the head guard, we have to look for the entry with C100. So we go to the next node, A50. It's not this one, it is the next one, which is C100. So we'll have to remove this one, right? So we delete this node, and we have to relink the broken links, right? So from A50, this should go to the B25, and from B25 this should go to A50 here, and then this links here should also be deleted since the C100 node is not existent anymore. So we have deleted the C100 and relinked from A50 to B25. Okay, so yeah. And then what if we were to find A? Okay, so to find A, we have to again start with the head guard, and then Well, luckily enough, we found an entry with key A at the first one, so we'll just return this one, this entry A50. If we find D, however, we start from the head guard. A50, A is not D. Next is B25, it's not D. B50 is not D. A50 is not D. Well, D30 has the key D, so we'll return this entry, D30. Now if you find X, still the same process. Start from head guard, A50, B25, B50, A50, D30, and then go to C50, and then until you reach the tail guard, and still you have not found X, so you'll actually return null, since X does not exist in the dictionary. And then for find all B, it will go through the dictionaries, also the DLL, and then it will return each time you find a entry with key B. So if we just clear out everything, okay, I'll just use a different colored one. So if we start here from the head guard, is this B? No. Is this B? Yes, so we'll return this one. So B25, and then for the next one, B50 is also B, so B50, and then go to A, it's not B, it's not B, go to C, it's not B, and then go to tail guard, so we've reached the end. So these are the only two entries that will be returned. Okay, so that is how the DLL dictionary works. Okay, so let's clear this out for now. Now, how about the performance of the DLL dictionary? So for insert, it's faster now compared to the DLLMap, because you don't need to make sure that the key is unique, right? So you can just insert at the front or the back, and this will just take constant time, O of 1, since you can just link it with the tail guard or the head guard, whichever you prefer. And yeah, so that will just take maybe like four steps, right? So link the new node to the tail guard to the new node, and then the new node to the previous last node, and then the last node to the new node. Okay, so it will just take constant time. However, finding and removing still needs to traverse through the DLL to look for the entry with the given key, just like what we did, right? So it will still take O of n time. Okay, so remember earlier when we tried to find or remove entries with a given key, we needed to traverse through the whole DLL, and in the worst case you will reach the tail guard, so you've gone through the whole DLL, so that would be O of n, okay, where n is the number of items in your dictionary. Okay, so it's still in linear time. And for the memory, it's also O of n, because of course you need to have one DLL node for each dictionary entry. Okay, so 1:1. That means that if you have n entries in the dictionary, you also need n DLL nodes. So you have O of n for your memory. Okay, so it did improve on the DLLMap's insertion, because we did not need to make sure that the key was unique. However, the find and remove still runs in linear time. So the DLL dictionary implementation is only effective for small dictionaries, or if insertions are common, since it runs in O of 1, while the search and removal methods are rare. Now, when does this happen? So for example, if you're doing an application for a login history to a lab computer, so for example, your key would be let's say lab for computer number 1, and naglog in si, let's say, user A, and then another entry would be for lab for computer number 2, naglog in si user B, and so on. So it's just a login history to the lab computers. So insertions are common because you'll just basically add an entry each time someone logs into the computer, whereas search and removal are rare. So maybe you don't really remove entries, if at all, because this is a log file, so you don't usually remove entries there. And for search, it also rarely happens. Maybe you only search through the log file if maybe something wrong happened, like maybe the computer crashed or something, and then you try to look up who was the last user to use this computer, right? So, but this rarely happens, whereas for insertion, this is pretty common, because each time a user logs into the computer, then it would add a new entry. Okay, so that would be one example maybe of when the DLL dictionary is effective. Okay, now how about if we used an unsorted array instead? So instead of a DLL for the dictionary, what if we use an array, right? And it turns out it will still have the same problems, right, as we did in the DLL dictionary. And to show you, here's the same example, but instead of a DLL, we used an array. Now let's go through these methods here to make sure that they are indeed doing the same thing. So for insert C50, we'll just add it to the end because there are no restrictions on keys being unique, so just add it to the end, right? And then for find A, so this takes O of 1 because you can just add at the back, right? Earlier in the DLL, we could add at the front or at the back, but this time in array, we need to add at the back, because if we add at the front, we need to move items backwards, so that would be unnecessary. So you just add at the back so you don't need to shift items. Now for find A, well, you can find one here at the first one, so it's fine. But if you find D, you start at index 0, and then is this D? No. Is this D? No. Is this D? No. Is this D? No. Is this D? Yes. So you found D30, so you return that. But you've essentially gone through the whole array, you've traversed, so this takes O of n, right? And then even worse is if when the key does not exist. So find X, so you start at index 0. Is this X? No. Is this X? No. No. X. It's not X. It's not X. It's not X. And you've reached the end of the array, so you'll return null, right? Since X was not found, as this is also O of n, right? And then for find all B, you also need to traverse through the whole array just to return these two items that are in the middle, because you don't know what if there is a B entry here somewhere, right? So you don't stop midway just because you found some B entries, because you need to find all B entries. You need to go through the whole array to make sure that you've returned all B entries, right? And then one more thing when dealing with arrays is that if you remove C100, which is right here, so to remove this, you need to search for it first, right? So is this C100? No. On the next one, it is C100, so you'll actually remove this. But there will be a hole in index 1 if you remove this, so you'll actually need to shift items forward again just to make sure that there's no hole in your array. So instead of just having O of n for the search, you also have O of n because of the shifting of items. So even if you find your item at the front here, then you'll have to move all items forward, so that will also take O of n. Okay, so in effect, DLL dictionary is even better than ArrayDictionary, because if we remove for DLL dictionary, we just had to, like, if we remove this node here, we just had to relink the neighboring nodes. But if we use the array, if we remove this item here, then we have to move all items forward, right? Which is more work to do. So yeah, even if we used or even if we switched out the array for the DLL, it still had the same performance. So insert is O of 1 and then find and remove is O of n, because you need to traverse the array or the DLL to accomplish your task. So you've noticed so far that we did DLLMap, we did ArrayMap, we did DLLDictionary, and we did ArrayDictionary. And it turns out that even when we switched between DLL or array, the performance was the same, and then the same thing here. What if that is not the problem? What if the DLL versus the array is not the problem? What if this one is the problem? The fact that it is unsorted. Okay? So, what if we try sorting the entries in the array? Okay? So, the last implementation will do exactly that. So, the last implementation that we'll look at is called the search table, which will try to implement the dictionary using a sorted array. Now, you can also use this for the map, but for it to be more general, we can just look at the dictionary here. So, the search table will be using a sorted array. Okay, so we'll store the dictionary entries in the array, where and while storing them, we need to sort them by their keys. Okay, so how will that happen? So let's say that we have this dictionary here. So it's the same dictionary that we've been using in our examples earlier. So A50, C100, B25, B50, and so on. So instead of adding these entries in this arbitrary order, we will add them to the array, but we will sort them through their keys. So you'll notice we have A50, A50, B25, B50, C100, C50, D30. So they are now sorted by their keys. So A, B, B, C, C, D. Okay, so that is how the search table will look like. Okay, and let's see if this will improve our performance. Okay, so for the performance of the search table, find can actually run in O of log n. And remember, log of n is better than O of n, right? So we can do this because we will use binary search to look for the key k. And this is possible because we know that the array is sorted. Okay, so remember your binary search from, I'm sure you've already discussed this in one of your previous ComSci courses, but to review, how does binary search work? So binary search works under the assumption that you have a sorted array. Okay, so you have to make sure that the array is sorted. Okay, because otherwise it will not work. So how will binary search work? So you have a middle element here, which is the item in the middle, and then you have a pointer to the low end and the high end. So let's try to look for the item number 2. So how does binary search work again? First, you look at the mid. Okay, so you're looking for 2, right? So 5 is greater than 2, right? So 2 is less than 5. So that means that 2 should be to the left of the middle, right? So it should be somewhere to the left if it exists, if it does exist on the array, right? So what will happen is we will change our range. So instead of searching from 1 to 9, we will just now search from 1 to 5. So this will be our new high. Okay, so this will not be the mid anymore, and the mid will now be 3. So we're now searching from 1 to 5, and we're now disregarding this. Why is that? Because since it's sorted, and we know that the middle part is 5, and 5 is greater than 2, so this part here is already useless. So we know that 2 is not found on the right part, because on the right part, that would be greater than 5, right? So since we're looking for less than 5, which is 2, so we should focus on the left part. Okay, so now the high pointer is at 5, and then the mid is at 3, so we'll do the process again. Look at the mid. Well, now 2 is still less than 3, right? So we'll focus on this half right now, so we'll make this the high part, okay, and then we'll disregard these parts here. Okay, so low is 1, high is 3, and then the mid would be 2. And this time, when we search for 2, it's already at the middle. So we have found it. So how many iterations did it take? We only took 3 iterations. So we looked at 5, we looked at 3, and then we found 2. So it would be 3 iterations. Now, if we just went through it linearly, we would have done it in 2 steps, but it would be better if, let's say, for example, on the next example, so let's clear this one. Let's try 5. If we go through it linearly, it will take it 5 steps, right? So 1, 2, 3, 4, 5. You found 5. But if we do it in the binary search, if you start at the mid, you've already found it right away. Okay, so that was faster. Okay, now how about for let's say 7. So instead of 9, let's try 7 first. Okay, so for 7, we'll do it again. So 5 is the middle part. So since 7 is greater than 5, so 5 is less than 7, so we should focus on this half right here to the right and disregard this part here. Okay, so we'll make this the low end, and then the mid would be somewhere here, and then we'll find it in 2 steps, right? So from binary search, we found 7 in 2 steps. If we did it linearly, we would have found it in 7 steps, because we have to traverse 1, 2, 3, 4, 5, 6, 7 steps, right? But using binary search, we found it in 2 steps. Okay, next let's try what will we try next? How about 9 this time? So for 9, we start with the mid 5. Oh, that's too big. So we start with 5, and then since 9 is greater than 5, so we'll focus on the right end. So this will become the low part, and then the mid would be 7 here. So 7 is still less than 9, so we'll focus on the right part again. So this will become the low, and then mid would be 8, but 8 is still less than 9, so we'll focus on the right part. So this will become low, and then high, and then the mid would be 9. So if you have 9 here, then you've already found it. Now what if it does not exist, like for example 13? So we'll do the same thing. So from 5, it will go to 7, and then it will go to 8, and then it will go to 9, and then after that, you'll see that the low and the high would be aligned, and then if you adjust it still to the high would be, you'll find out that the 13 could not exist in the array, because you cannot adjust this anymore since high and low are already the same thing. Okay, so that's binary search. So I'm sure you've already learned this from your previous ComSci courses, but again, you need to make sure that the array is sorted, and binary search runs in O of log n time, so that's why we could do find in O of log n time. Okay, now how about for insert? For insert, it will still run in O of n time, because we need to find the correct place to insert the entry into to keep the array sorted. So to do that, we'll use binary search, but to insert, before inserting the entry into the spot, we need to shift items to make room for the new item. And in the worst case, that would take O of n. Okay, so let's see an example. What if we tried to insert a new entry here, which would be, let's say, A25. So to do that, we would need binary search to look for the correct place to insert this into. So where can we insert index the entry with key A? So we'll start with the middle, which is in this case B50, right? But A is less than B, so we'll have to go through the left part. Okay, so go through here. A50 is the new middle, and A50 is correct. It's the same one, so we can insert it here, right? So we'll have A50 here and A50 here. So we'll insert the A25 after index 1, right? But so it should be in index 2, but index 2 has B25. So what will happen is we need to shift all these items forward first before adding A25. So we have D30 here, C50, C100, B50, B25, right? So you'll notice that they moved one index forward, all of them. And since there is now a new hole here, that is where we can insert our new entry, which is 825. Okay? So this takes O of n, because at the worst case, what if you need to add in here, in the first slot, right? So you need to move all entries forward to make room for this new entry at index 0. Okay? So that is why insert still takes O of n. Okay? So insert is still O of n. How about removal? For removal, it also takes O of n, because before you can remove the entry, you need to look for it, again, using binary search. So binary search only takes O of log n. However, after removing the entry, you need to shift items to fill the hole after removing it, right? So what will happen? What if, for example, we need to look for, let's say, B25. So remove the entry B25. Okay, so using binary search, we'll start at B50, which is the middle, right? B is the same key, so it must be to the left or to the right. And then let's say started at A50 as the new middle, but since A50 is already less, so you'll go back to the right, so that's when it will find B25 in binary search. So you will remove this one, right? But then there will be a hole on index 2. So A50 will still be in index 1, index 0. A50 will still be in index 1, but there is a hole in B25, so you'll actually need to move all of these entries forward. Okay? So B50 will now be in the index 2, C100 will be in index 3, C50 will be in index 4, and D30 will be in index 5. So you'll notice they moved one index forward, right? So that is why removal still takes O of n time, because at the worst case, what if you needed to remove this entry here? So you'll have to move all items forward, right? So that is why it's still O of n. Okay, so yeah, that is the search table. For the memory, it will actually take more memory, O of C, wherein C is the array capacity. because remember that if we use an array, we need to predefine its capacity. So let's say in here, we predefined it to a capacity of 8, so that's why even if there are only, let's say, 7 entries, the capacity is still 8. Okay, so the memory that we'll use is O of C, wherein C is the array capacity and C should be greater than or equal to n, which is the number of entries in your dictionary. And this would be wasteful, of course, if you have a capacity of a big capacity, let's say 1000, and then you only have 3 entries in your dictionary, right? Because you are setting aside 1000 memory units when you're only using 3 entries, right? So it would be wasteful. Okay, so this implementation is only effective for small dictionaries, and it's also effective when the search part is common, so you're always searching, but insertion and removal is rare. Okay, so for example, if your records, if your dictionary is already set, I mean it's not you're not planning on adding or removing more items to it, and you're just like you just want to search through some of the entries, then search table would be an effective implementation, because if you sort the entries, then you can make use of the binary search, which will make it run in O of log n time. Okay, but if you commonly use insertion and removal, then it would still take linear time of O of n because of the shifting around. Okay, so that's it for search table. Now, earlier we have been asking what if we use array after discussing DLL, right? So we started with DLLMap and DLLDictionary, and then we asked what if we used an array instead. So this time we'll flip the switch, and after using a sorted array, what if we used a sorted DLL? Can we use binary search to do it also effectively? Now, the problem with using a sorted DLL is that okay, so we have the example here, right? So let's see. So the thing that makes it work for an array with the binary search is that you can access the indices right away, right? The index. So you can have the access to the mid index, the low and the high. You can update them. And how do you know the mid? So the mid is basically low plus high minus low divided by 2. So for example, if you have right now, if we still don't know what the mid is, the low currently is 0, low is 0, high is 8, right? So the mid would be low, which is 0, plus 8 minus 0 over 2, which is 4. So 0 plus 4 is 4. So that's why the mid index is at 4. Now, for example, what if we are searching for 2, right? And we found that 5 here is greater than 2. So what would happen is this would become the new high, right? So what would be our new mid? So if our low is index 0, our high is index 4, then this would be 0 plus 4 minus 0 over 2. So our new mid would be index 2, which is right here. So this would be our new mid. Okay? Now, what if it were on the opposite half of the array? What if, for example, we were looking for search for 8? Okay? So if we look at mid 5, we know that 5 is less than 8, so we have to make this be the low end, right? And then to find the middle, the low now is 5 plus high minus low, so that's 9 minus 5 all over 2. So this is 9 minus 5 is 4, over 2 is 2, so 5 plus 2 is 7. So our new mid would now be index 7 right here. Okay, so that is how you find your middle index, and that is doable because we are using an array wherein indices are readily available. But what if you are using your DLL? Now, for DLL, remember that you only have access to the head guard and the tail guard, which are your sentinels. Now, how will you get the middle node? Well, you can, but you need to traverse from here to here. And if you know the size, for example, I know that the size is 9. So 9 over 2 is 4.5, right? So maybe if I take the floor, this would be at 4. So I just need to make 4 jumps from head guard. So 1, 2, 3, 4. So I'll make this the mid for now. Or no, let's take the ceiling, just so we have the same mid as the array here. So 9 over 2 is 4.5. So if I take the ceiling, this would be 5, right? So I need to make 5 jumps from the head guard. So 1, 2, 3, 4, 5. So this is the mid. But it took us 5 steps just to get to the mid. Whereas in here, we just need 1 step because you just compute for the mid using this equation, and then you can jump right away to the mid element, right? So in here, it's not effective because you have no direct access to middle elements right away. Okay, so you don't have indices that you can directly access certain cells directly. So you just need for DLL you have to traverse using the next and previous links. So in this regard, DLLs are weaker than the arrays. Okay, so earlier in the DLLMap and the DLLDictionary, we said that they were better than the array versions because in the array we had to shift items forward, right, or backward. But in here, array is actually better than the DLL because in arrays you can access middle elements right away, whereas in DLL you have to traverse. Okay, so you can use DLL, but it would not be efficient. Okay, so if you want to use binary search, use the array implementation. So that would be the search table. Okay, so that's it for the implementations. So let's try to compare the implementations that we discussed so far. So for DLLMap and ArrayMap, so it didn't really matter whether it was DLL or it was array, as long as it's unsorted. The search, delete, and insertion will take O of n time because you need to traverse the DLL or traverse the array to make sure that the key does not exist already, or to look for the key basically. Okay, and additionally, if you use array, you need to shift items forward on deletion to avoid having holes in your array. The same thing for DLLDictionary and ArrayDictionary. As long as they are unsorted, then they will have the same running time for search and delete, which is O of n. But for insertion, it will just take O of 1 because you can just add the new entry at the back or at the front of the DLL, or for arrays, you can just add it at the back of the array, right? Since you don't need to make sure that the key is unique. Okay, so however, it's still O of n for search and delete because you need to traverse the DLL or traverse the array to look for the certain entry that you are looking for or you're deleting, right? And additionally, again, if you are using array for the dictionary, you need to shift items once you delete because there will be a hole that's left. And finally, for the last implementation for search table, this time we used a sorted version of the entries using an array. And this time, because we used a sorted array, you can use binary search to make search run in O of log n. Okay, but deletion and insertion still runs in O of n because you need to shift items after inserting at the right position. So you need to make room for the correct position, and then after deleting, you also need to shift items to avoid having a hole, right? So those are the implementations so far that we've discussed. Now, right now, the implementations for map is not really that good because it's all of the methods run in O of n. So in the next video, we will discuss more implementations that will make the performance better. So we'll be using hash tables and skip lists in the next video. Okay, so that is it for this video. So to review, we talked about entries, right, which are key value pairs. So value is the one that you need to actually save, whereas key is the like the tag, or the key that you need to use for searching the entry. Okay, for the map ADT, we need to ensure that the keys are unique, but for the dictionary ADT, you can allow the same keys for multiple entries. Okay, so both of them use entries, and then they have the different methods for searching, insertion, and deletion of entries. And then we also talked about the implementation of the map and dictionary using DLL and the search table implementation. Okay, so as I mentioned earlier, our next topic would be hash tables and skip lists, which are more implementations of the maps, which would improve on our current implementations using just DLL. Okay, so that would be for the next video. So that is it for this video. And if you have any questions, please don't hesitate to ask me, and I will see you next time.